Thanks, Andrew. Good morning. It's great to speak to you today. The last couple of days, I've met and heard so many talented people. Just being here is an inspiration and an honor. As you can all see, the leaves are starting to change color now. This makes it a perfect setting for my presentation this morning. When I was on a winter hiking trip, I noticed something about the shape of tree branches. At first, all I could see was a mess of tangled branches, but then I noticed a pattern. I took pictures of different branches of different trees, and the pattern became clear. I noticed that the pattern grew in a spiral pattern. I noticed that the branches grew in a spiral pattern. I wondered whether there was a formula behind the shape of tree branches, and if so, why they exist. To answer the question, I built test models to investigate how trees collected sunlight. I found a new way of arranging solar panels that may increase sunlight collection. My investigation started with understanding the spiral pattern. I found the answer in the work of a medieval mathematician, Fibonacci. Fibonacci played with a math puzzle to figure out how fast rabbits could reproduce over time. Fibonacci invented a mathematical pattern. Starting with 0 and 1, Fibonacci added two numbers in the series together, and the sum became the next number in the sequence. The number sequence looks like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Today it's called the Fibonacci sequence. What's amazing is that the Fibonacci number and its ratios appear in many forms of nature, like the shape of nautilus shells, the seeds of a sunflower, and galaxies flying through space. Even ratios of parts of your body follow the same pattern. Trees are no exception. Tree branches follow a Fibonacci formula. The oak tree has a Fibonacci fraction 2 to 5, which means that 5 branches spiral around the trunk 2 times to reach the same starting point on the trunk. Different types of trees have different types of patterns. For example, the elm tree, which is 1 to 2, the beech tree, which is 1 to 3, the willow tree, which is 3 to 8, and the almond tree, which is 5 to 13. But I still wanted to know, why do trees use this pattern? I had the hypothesis that since the main job of leaves is to process sunlight for photosynthesis, that had something to do with gathering sunlight. To answer this question, I designed and built my own solar panel test models, following the Fibonacci pattern of an oak tree. I copied the Fibonacci pattern as closely as possible. I also wanted to discover how the tree design compared to common solar panel designs, so I constructed a flat panel array. I used data loggers in the computer to record how the models were doing. Since I wanted to monitor the collection of sunlight, I collected data on voltage, but I also checked for current. I ran my tests for several months. The results were really surprising. The Fibonacci design recorded 20% more open current voltage and collected up to 2.5 more hours of sunlight during the day than the flat panel design. But the most interesting results were in December, at the winter solstice, when the sun was at a low point in the sky. The Fibonacci design collected sunlight up to 50% longer over the day. I discovered the Fibonacci pattern can allow a tree to track the sun better as it moves through the sky. My results suggest that the Fibonacci pattern can improve solar panel arrays in several ways. It collects more sunlight when the sun is at a low angle in the sky. This may prove useful for winter months in extreme latitudes. It takes up less room in urban areas where space is tight. It is not affected as much by shadows. It does not collect rain, dirt, and snow as much as the flat panels. And it looks a lot nicer. My project generated a lot of reaction from people around the world. Many people were excited about the idea. Others had great suggestions to make my research better. There are even some people who saw money in it and tried to be my friend on Facebook. I think I'm the only 13-year-old in the world to have venture capitalists friend me. The internet allows people to share ideas, but people will be people, and the media will be the media. And the lesson I learned is that sometimes the internet is not a substitute for scientific peer review. I'm continuing my research, and I'm now studying why there are different Fibonacci patterns in different species of trees. I'm discovering that leaf shape is related to the Fibonacci pattern too. I'm using suggestions from different sources to improve the design. My current project is a large-scale Fibonacci array, which has been adopted by a family of chipmunks as a hangout. But most importantly, I'm sharing my ideas on solar panels with others to build a better tomorrow. I've been asked to work with the Resilience Research Center in Madison, Wisconsin, to design Fibonacci arrays that middle school students can use for research. I'm also collaborating with a professor of design at Purdue University to create a Fibonacci array that combines technology with functional art. My goal is to get people thinking about new ways to improve solar technology. My research is just beginning, and there are many challenges ahead, but my experiences have taught me to never give up. I want to thank Andrew Zoli and PopTech for this opportunity, and for all of you for your support and interest. Thanks.